Last week, we started looking at universal coding, where, uh, so we started looking at universal compression, where we wanted to compress symbols coming from a distribution without really knowing anything about the distribution. And we introduced this notion of min-max redundancy, Rn star. Let me write it in a slightly different color. So Rn star, which was defined as minimum over all possible codes that you can think of, all possible prefix free codes. And so C is a prefix free code. Maximum over uh, maximum over all PMFP on the alphabet X. And then after that, you take expected value under Pn, NIID random variable generated by P, of the average length that the code assigns under P, minus the best average length that any code can assign, even when they know P. So you are trying to compete with this code which knows this scheme which knows a lot more, which knows the exact distribution, and you're trying to come up with a scheme which, in the worst case, is competitive with this scheme. So this is what this Rn star is. And first thing we noticed was that this Rn star is related to another quantity related to a slightly different problem, the probability assignment problem, which we call Rn star. This is minimum over all distributions Qn that you put on n-fold alphabet, not necessarily independent distribution. Maximum over all PMFP on the alphabet X. The divergence between Pn and Qn. And what we noticed was that so one result we saw last time was Rn star is less than equal to capital Rn star plus 1, and it must exceed capital Rn star plus 1. Sorry, capital Rn star. Okay, this is the main observation. So one implication of this observation is that we might as well just solve the probability assignment problem, this one, and then that will give you the best. That one implication is mathematical, that this quantity and this quantity are almost the same, and one implication is algorithmic. And it says that if you look at a code which assigns code length symbols of lengths proportional to log 1 by Qn, okay, that's like the Shannon code for this guy. Suppose we find a code which assigns lengths of log 1 by Qnx. So that's the Shannon code corresponding to Qn. For such a code, the average length under any Pn, for such a code is, this is some calculation we did last time, and this can be written as the divergence between Pn and Qn plus NHP. Okay, so this is the extra cost. This first part here is the extra cost that you pay because you use the wrong distribution, you didn't use P. Okay, but if you minimize this extra cost, that's what this quantity is doing, then the performance that you get is actually anyway best min-max performance in terms of gap to NHP. That's what this result says. So one possible algorithm for finding a universal code is to use this Qn, the Qn which attains this min-max value, or approximately attains this min-max value, and use the Shannon code for that Qn. However, last time towards the end, we saw a different kind of scheme. We didn't use this Qn. We used what we were calling a type or word frequency based scheme, where where the scheme was that for each symbol we count how many times that symbol appears in the sequence, and that determines the type of the sequence, this frequency vector. And we store frequencies of all type in some enumeration, and we point out what's the type and then what's the enumeration of this given sequence in all sequences of that type. That was the scheme. So in particular, for the case of binary alphabet, you first make these different tables corresponding to different number of heads in the sequence, and then you go to the table with these many heads, the heads of the current sequence, and find the index of the sequence and store that index. What we showed for that scheme was that the performance of that scheme, maybe we call it something RNC. Okay, I'm just calling it RNC, defined as max over P, expected value over Pn of L of xn, x1 to xn minus nh. So we saw that for this particular scheme, the type-based scheme, RNC is, which is obviously more than the min-max scheme because you can in general do better. We showed that this is less than log n plus 1 cardinality of, let me make some space for myself, cardinality of alphabet minus 1 times this. Alright, and in fact, I claim that you can improve this by a factor of 2. I never showed you that calculation. It's a more elaborate calculation, but I just believe it. Just take my word for it now. And this is optimal. This is order-wise optimal. The next term here, there's a lower bound which matches this. The next order term can be smaller, but the first order term, this is optimal. Okay. Now, this was a type-based scheme, which was not really a practical scheme because how would you really enumerate all the sequences with a given type? There are exponentially many sequences of that type, exponential in the length n. So this is not practical. Also, what is instructive is to think of, can we think of the probabilities that this scheme assigns? So if you remember the proof of this result, with each scheme we can also associate a probability and a probability based scheme. So in this scheme, the length of the symbol corresponds to first choosing first the log of number of types, and then the number of bits required to represent all sequences in that type. So the effective probability Qxn that you associate with this is the following. First, you randomly generate a type. I'm describing a Qxn, so maybe I'll write it here. Qn associated with the type-based scheme generate a type uniformly from the set of all types, and then the next step is generate a sequence uniformly from the type set for type found in step 1. So the difference between this algorithm, what I'm saying here, and what I've described here is that this is just generating probabilities. So you can view the length assigned by this scheme as corresponding to log 1 by q and x for this probability distribution. This is just to tell you that probability assignment and scheme are equivalent, and we saw this equivalence in this proof. So when you give me a scheme like this, I can find a probability assignment also corresponding to it, and this is that probability assignment. Okay. All right. So now we have seen this type-based scheme. It's not practical. We can force ourselves and let's say in some convoluted way think of a probability that we can assign corresponding to that scheme. But actually, there are practical schemes which start by assigning this probability, and it is instructive to think of how those probabilities are assigned. Okay, and this week we'll see such schemes which are based on this probability assignment. Practical schemes